Hello, in this video, we will introduce tail recursion. A tail recursive function is efficient for reducing stack space. So let's see, what is a tail recursion? Tail recursion is this. When you invoke this function here, you don't have to come back because that's the end it returns. So this function A is a tail recursion. So here for function B, so you invoke function B recursively, but after this call is finished, you have to come back because there's more work to do. So this is non-tail recursion. Let's look at the examples we have in this chapter. The is pattern drawn function is tail recursive because once you return true or false, that's over. And the factorial function is not a tail recursive. So look at this factorial function here. So because when you finish this, you invoke this factorial n-1 here. So after this finish, you have to perform additional operation. Here is n times the result from this return. So it is not tail recursion, but we can modify this program to make it tail recursive. So this is what we're going to do is here is this is factorial. So we're going to have this factorial n is to invoke this helper function factorial n1. So what is this n1 here? This is here. It's a result. It is a result. So this result here, we're going to look at this result. If this n is 1, so we're going to return the result. Result is accumulating all the multiplications for obtaining the factorial so far. So this one here, look, you can see this is the implementation. If it's not 0, so what I'm going to do, so I'm going to have this result times n. So let's see how a tail recursion is implemented. Compiler can optimize tail recursion so that for the tail recursion, when you have a function call, you don't have to create an activation frame because there's no need. Once you don't have to create additional, so you can use the existing activation frame, and once it's finished, you don't have to return back. It's all done with a return. So I'm going to copy and paste this and see here. This is, I'm going to look at the animation. So here is the animation for this tail recursive version of factorial.
The program starts the execution from the main function and the main function is pushed to the stack.
So this main function now, this is invoked. It's now on the stack.
The statement displays a message to prompt the user for input.
So I'm going to enter 3.
The statements prompt the user for an input. Read an input 3 from the console and assign it to variable n. The program invokes factorial n. Factorial 3 is invoked and pushed to the stack. The value of n in the main function is passed to factorial.
So now invoking factorial. This is here, factorial 3. So this is the one. Now the next.
The program invokes factorial n1.
This is the helper recursive function.
Factorial 3, 1 is invoked and pushed to the stack.
This is pushed on top of the stack now.
The statement tests if n is equal to 0. It is false since n is 3. The program invokes factorial n-1 n times result.
Now, compiler recognize that this is a tail recursion, so it does not create an activation frame. So this is just override on this existing activation frame. Now you see the result.
Factorial 2, 3 is invoked. Since factorial n result is tail recursive, the compiler does not create an activation record for this call. It will use the activation record on the stack.
So this is the one here. We have this result is 3 now.
The statement tests if n is equal to 0. It is false since n is 2. The program invokes factorial n-1 n times result. Factorial 1, 6 is invoked. Since factorial n result is tail recursive, the compiler does not create an activation record for this call. It will use the activation record on the stack. The statement tests if n is equal to 0. It is false since n is 1. The program invokes factorial n-1 n times result. Factorial 0, 6 is invoked. Since factorial n result is tail recursive, the compiler does not create an activation record for this call. It will use the activation record on the stack.
So now please note that n is 0.
The statement tests if n is equal to 0. It is true since n is 0. The statement returns result. Since the function is tail recursive, this return statement will exit factorial n result function.
So that is over for the recursive call.
Factorial 3, 1 returns 6 and it is removed from the stack. Factorial 3 is on the top of the stack.
So returns back to this function.
The statement returns 6 from factorial 3. Factorial 3 returns 6 and it is removed from the stack. The main function is on the top of the stack.
So now the main
The
function
statement displays the result.
displays this result.
The main function is finished and removed from the stack.
Return, the main function is finished. So this is tail recursion. Tail recursion is efficient. A lot of applications we're going to see using recursion in the future, you're going to see they're going to be tail recursion. They are very efficient. That is all for this section on tail recursion. See you on the next video.